Let us continue our discussion on the AASHTO method of payment design, and in fact in this method there are different levels of design that are used. So, what is really called as level 1, level 2 and level 3. In level 1 you are going to basically measure all the input parameters directly for each and every payment design. So, that means you are not going to use any tabulated values, you are not going to use any historic data. Level 2 is slightly less important. You will be estimating these parameters from regression equations. For instance, you may not really want to measure the modulus property of a bituminous mixture, rather you will use some predictive equation. So, that means you have some idea about what could be the modulus value for a range of temperature and frequency from some of this predictive equation. And in level 3 these are all basically based on default values. So, you can think of this level 1 design more in terms of within the Indian context, national highways, expressways, to some extent even state highways. Level 2 will be more in terms of district roads and to some extent some of the state highways, and level 3 is more in terms of the minor roads. Okay. So, that is the idea, and now what we are going to do, we are going to talk about traffic, material characterization. After that we will talk about how the influence of environment, stress strain behavior and distress are interconnected. So, let me write it here: traffic, materials, environment, stress analysis, distress, and I will also show you some sample distress limits. Okay. To give the due credit that they deserve, AASHTO or the MEPDG current version is the one that actually put together the traffic in the most rigorous platform. Okay. So, let us take a look at each of these things. If you are watching this lecture, I request you to pause and write these definitions. So, first and foremost thing is the axial load spectra. So, this is the distribution of axial loads for a specific axial type. So, you are talking in terms of determining the statistical distribution. Then comes the hourly distribution factor, percentage of trucks using a facility for each hour of the day. Now, this is going to be used later in the distress computation, and so this is where MEPDG relates traffic to the material, to the environment, to stress analysis, and finally brings it to the distress. Okay. So, now you will understand how comprehensive this is. Now, to just give a simple example, let us say you use this load equivalency factor and then you come out with a 30 MSA. Now, someone can ask you, okay, this is all fine, this 30 MSA is for 3 years. So, let us take 1 month and let us say we are going to have something like 0.1 MSA. Now, where is this 0.1 MSA applied? Morning, afternoon, evening, because what will really happen, depending on the temperature, depending on the spatial location, the modulus values are going to change. If the modulus values are going to change, the strains are going to change. If the strains are going to change, the damage is going to be different. So, without even making that complete connection, how is that we are trying to compute the damage? So, now it will strike you like saying that, oh, this is how I should have ideally carried out the payment design. You will do that. Then comes the monthly distribution factor. Now, interestingly, what MEPDG will do is to relate this monthly distribution factor with the temperature variation also, and this is a very important parameter, what is called as the normalized axial load spectra, normalized histogram of axial loads for a specific axial type. So, when you say use the word normalize, what is that you are trying to do is you are trying to create a common platform. Okay. So, when you create a common platform, it becomes easy for you to compare across different axial type, that is the whole idea. So, what it means is number of axial applications within a specific load range for an axial type divided by the total number of axles weighed for that particular axial type. That is your normalized axial load spectra. To just give a example, this is from this published paper, you can say this is a single axle, dual, tandem. So, if you take a look at this, this is the way in which for different types of vehicles, class 4, class 5, 6, 7, class 8, 9, 10, this is the variation that you see. Now, each of these classes, to just to give an example, so let us take this one. Each of these classes will have different vehicles, different type of different number of vehicles. So, what you are now trying to do is when we want to put all of them in one platform, because we want to find out what is the axial load versus the what is the percentage axial. So, if class 8 had let us say 100 vehicles, class 9 had 50 vehicles, class 10 let us say had 20 vehicles. So, what we will do is now go back to the previous definition, number of axial applications within a specific load range for an axial type divided by the total number of axles. So, that is what we are trying to do here. So, trying to divide it by the number. So, if you are really looking at dual, so this whole thing, the middle one corresponds to the dual. So, what you want to say here is 30% falls within this range, 15% falls within this range, maybe 12% falls within this range. So, this is the normalized axial load spectra. Now, comes the next classification, what is really called as the truck classification distribution. So, distribution of the number of truck applications for each truck classification for all the trucks counted. So, let me reiterate, AASHTO will not do load equivalency factor. AASHTO will take all the trucks for which you are collecting the data from the field and apply it in the pavement and then try to compute what is the damage for each and every axial application. So, if it has to do all those things, then all the truck that your data that you are collecting have to be classified into different categories and a different distribution. So, we also have what is really called as the normalized truck classification distribution. So, that is a normalized distribution of the different truck classes within the traffic stream. So, let me just give a simple example. Okay. So, truck traffic classification group means, see for instance, if you take let us say major single trailer truck route, major single trailer truck route type 1, type 2 and it could be some other type here which will come in 1, 2, 3. Now, what you are saying that these 4 to 13 that you see are the different truck types. So, if you go and search, or I can even share materials with you, is truck class 4 will have one combination, truck class 13 could be something like your dumper trucks. So, what you really need to do is, if you take any truck route, okay, that truck route is going to have almost these many trucks here, and it will be interesting for you to note that this one class 9 has major proportions. Similarly, if you come to TTC group here, you see that this number has reduced, whereas this number seems to be slightly more here, and this is more or less the basic idea with which that these groups are created. So, now to understand index type number that defines a group of roadways with a similar normalized axle load spectra and normalized truck volume distribution. So, to just let us say you are talking about NH 45, and let us talk about some other NH 1. Now, each of this highway have different characteristic. I have mentioned this before. So, if you are a pavement designer, it is necessary for you to understand what type of highways that you actually have. What kind of highway is this? If it is going to be NH 45, it may be one kind of a highway that carries raw material from one place, sends it to a factory, gets it processed, and from there it takes it to the port. So, that could be the characteristic feature of that particular highway. Now, what you need to do is to analyze the traffic that is going along this particular highway in terms of the different truck classes that are likely to be using that facility. See, because you already have different classifications permitted by IRC3. So, what you are going to say is NH 45's predominant feature is, this is the kind of category of trucks that are going to come. NH 1 predominant features will be some other category of vehicles. So, this truck traffic classification group needs to be necessarily carried out. So, this is the most important thing. So, the point is, if you have these kind of details worked out for the traffic part, then you do not really have any issue to analyze any national highway or state expressway as far as the Indian conditions are concerned. Now, why is that I am basically saying that? So, let us go back to this thing, level 1. Okay. So, you will basically say, for level 1 I need all the traffic data fresh, but if it is level 2, you will say that I do not really need all the data, all I really need to do is to find out what kind of TTC group and description that it falls under. So, once you know it, then most of the default values can be filled by you. That is the whole idea. Each highway has a specific distribution associated with it. The only thing that it can vary is probably the intensity of the peaks can vary or the volumes can vary, but the nature of the distribution is not really going to vary, and that nature of the distribution has to be determined by you. So, if you are going to take a look at this particular highway and then design it, all you really need to do is to find out what is the total number of vehicles, you know the percentage distribution. So, you will know the actual vehicle, and now you can do the monthly distribution also, because we have talked about the monthly distribution. So, let us say if you are talking in terms of this particular one, it is 62%, you want to ask how much is the monthly distribution. Then after that you also want to ask what is the hourly distribution. So, for every hour, every month, every year, for any specific truck, if you know what is the distribution, then doing the computation for the full year, taking into account the temperature conditions, material properties that change with respect to the temperature conditions, loads vary with respect to the hourly distribution, monthly distribution, you can integrate all of them and do the computation of damage. That is the whole idea. Okay. So, there are few other important traffic parameters that are mentioned, but not actually really measured. So, you can talk in terms of dual tire spacing. AASHTO also mentions what is really called as super single tire. And in fact, if you go and take a look at some of the trucks in the national highway, I am drawing something. So, let us say okay, you might have something like this. Now, these things might be lifted up or lowered depending upon the load that it carries, and these single tires carry lot more load than this one. Okay, so, these are called super single tires. As of now, Astoware will not consider it. Now, the tire pressure that they want you to use is 120 psi, that corresponds to around 827 kilopascal. Now, what is the tire pressure that is used in IRC 37? You may want to take a look at it, and you may also want to know that the actual tire pressure that is used in Indian conditions is lot more than what you will actually see. Okay. So, if that is the case, your strains are going to increase, the strains are going to increase, the damage is going to be accelerated. Then there is also something called as the lateral wander that you do. So, basically given any highway, you know the distance 3.5 meters or 3.15 meters. So, this is your location where you are going to have the axle repetition, and you can actually have construct a distribution here. Now, from the mean, what is the standard deviation? That is what is really taken by you as some kind of a wander. So, it could be 8 inches, it could be 10 inches, or it could be 12 inches. So, now we come to the next portion, which is what is really called as the material characterization. Now, what are all the materials that are allowed to be used as far as this Astoware is concerned? So, I will be talking only about the bituminous material. So, you can have SMA, you can have dense graded, open graded, asphalt stabilized base mixes, sand asphalt mixtures, and it could be central plant processed or cold in cycle in place recycling. So, now this technology could be with respect to foam or with respect to emulsion. Now, you can have chemically stabilized material, cement stabilized aggregate, soil cement, lime cement fly ash, lime stabilized soils, open graded cement stabilized aggregate. Similarly, when it comes to the non stabilized granular base and sub base, these are all the different types of mixes that can be used. The subgrade soil, the AASHTO classification is given here, A1, A2, A3, A4 and so on, and the bedrock details are given here. Okay. So, this is what is the material that are likely to be used here. Now, what are all the properties of the materials that you need to measure? Okay. As far as the new HMA is concerned, that is new pavement and overlay mixtures as belt properties prior to opening to track. So, this is dynamic modulus. Okay. So, we have discussed all of this in our material characterization of bituminous material. You can measure the tensile strength. Now, you need to understand these are values that are expected to be tested, not estimated, and these are all the AASHTO or the ASTM guidelines that are available here. So, this is Poisson's ratio, they want you to estimate it. You can leave this part, I will not be discussing this, I will not discuss this, I will not discuss this, because these are some of the things that will tell you to construct the heat transfer model that should be used for estimating the temperature within a pavement layer from the surface. Okay. So, these are all some of the things. The effective asphalt content by volume goes for the fatigue calculations, air voids, aggregate specific gravity gradation, unit weight, voids filled with asphalt. So, all of this go to the fatigue calculations. So, now you can understand these are the sequences that needs to be determined, and in fact, ideally all this information should be detailed explained in IRC 37. IRC3 should be part of it, FWD related information should be part of it, mixed design should be part of it, because when you are really talking about payment design, you are not really talking about payment design alone, you are talking about analysis of traffic, material characterization, distress characterization and everything. So, that is why the overall AASHTO payment design method that you see here, the green color book that I showed you here, maybe 180 pages, but the original AASHTO design guide with so many annexures and appendices and all those things runs to more than 2000 pages, right. So, when you are talking about an existing HMA in which you are trying to find out what is the structural capacity, you are talking about running an FWD and computing the back calculated modulus, Poisson's ratio is estimated, unit weight, asphalt content gradation, air voids and asphalt recovery. Now, similarly, different categories of material inputs are needed for level 2 as well as level 3. Now, let us come to the granular material. For the new experiment granular material, there are either two options are there. So, I am going to explain this little more in detail, though this would have been already discussed earlier. Now, this is the generalized MEPDG model that you are looking at. So, what is really called as the resilient modulus, theta is the bulk stress, this is the octahedral shear stress. So, the octahedral shear stress is computed using this formula. This is the normalizing stress that is used, and ideally this is the K1, K2, K3 or the regression constants. Now, so let us take a small break here to take a look at what exactly this is. So, now if this is your pavement layer, I am sure you would have worked out all these calculations. So, let us focus our attention on the second layer alone and let us look at different spatial positions. So, let us call this as E1, E2, you apply a load, okay. How much you want to apply? You want to apply something like, let us say if you follow AASHTO, you want to apply close to, let us say we will apply 900 kilopascal, why not, roughly, right. Now, when you apply this 900 kilopascal, you need E1 and E2 to estimate the stresses and strains, correct. Now, what you see here as the resilient modulus, it basically says these are, let me use a different color, K1, K2 and K3. So, you can leave this out, you can also leave this out, this can be taken as an normalizing pressure. So, what you are really looking at is theta and tau oct. Okay. So, how do we find out this theta? Theta is nothing but it is the trace sigma 1 plus sigma 2 plus sigma 3, that is what it is. And what is the octahedral shear stress? That is given as this particular formula which you are familiar with, right. So, what we can do is the following. How do we estimate this octahedral shear stress? I can estimate the octahedral shear stress if you know sigma 1, sigma 2, sigma 3. But for me to get sigma 1, sigma 2 and sigma 3, I need a material modulus, but that is the material modulus that I am planning to estimate using this equation. So, what I would do is, knowing K1, K2, K3, I might have an average value. So, let us say 600 MPa to start with. So, substitute 600 MPa for whatever value that you have got here, compute sigma 1, sigma 2, sigma 3 here, substitute it here as well as compute it here and estimate for given values of K1 and K2, K3 what is the value. So, you might get something like 640 MPa now. Now, what you do, come back here, substitute, use 640 MPa here, compute sigma 1, sigma 2, sigma 3. So, using sigma 1, sigma 2, sigma 3, determine what is theta, determine what is tau oct, substitute the values of K1, K2, K3, and you might get, let us say, 650 MPa. Then again you do it till such time you have determined that this is the modulus, and now use this modulus to compute your various strengths, right. So, what it means is, it is a iterative procedure, and this iterative procedure should be applied for every month, and in every month for the every hourly period where the temperature variation is going to change for every truck class. So, now you need to really understand the amount of computational effort that will go into this if such kind of models are used. You can do another thing, saying that look, there is not a big difference between 600 to 650 MPa. The amount of computational effort that goes into determining this load dependent or pressure dependent modulus is too much. So, what I would like to do is to get some estimate of the average modulus for the expected in place stress state. Okay. So, you are going to say that, look, I know what is the load that is going to come here. I also have some kind of an estimate of the stress state. So, what I will do, I will use the amount of stress state here and compute the modulus, but anyway I will use this modulus for all my stress strain calculations. So, this is the method right now it is being followed, but where do you think this iterative method has to be used? The iterative method has to be used when you are going to have this so called inverted payments, because in this inverted payment the material response is strongly dictated by the pressure that is engendered in that stabilized material. Okay. So, that will not be straightforward. So, I am not going to get into the details about the pros and cons of inverted payment. I have already discussed a little bit in detail when we were talking about the South African payment design and all those things. If you ask me, I am more a votary of a balanced payment. So, that means the modulus and the thickness variations should be gradual in such a way that the stress distribution can be controlled in the manner in which you really want, right. Now comes the next portion, what is really called as the three different things that I have related with the distress. One is called the sublayering, second is the climate, third is the layered elastic program that is used. This is called Jacob-Uzan's layered elastic analysis. Jacob-Uzan, Professor Uzan is a famous payment engineer from Israel. So, he was part of the MEPDG to develop this layered elastic program. So, now you take a look at this typical payment section. Now, you really want to know, can I just use the modulus values for one single section alone, or should I divide it into different types, and then for each of this I can have different modulus values. That makes sense. So, what exactly is the deal here? So, let us say I divided into two portions here. So, let us assume that this is topmost layer bituminous concrete. So, I have, call it as E1. So, call it as E1A, E1B, E1C. In addition to this, let me use a different color. this is your temperature variation across this thickness. So, the temperature here can be something, the temperature here can be something, and the temperature here can be something. So, depending on the temperature values, the modulus values can vary, and also due to the spatial locations, the modulus values can vary. So, if I do all these things, okay, so that means when I apply a load here, I need to compute this at each and every location depending on the spatial sublayering that you do as well as the modulus value that you change. So, to just give an example, this sublayering values also will change depending on the month in which you are doing your computation. So, let us say this is the summer month in which the temperature is substantially increased. So, the modulus value has decreased. So, you can actually see this is layer 1 and this is layer 7. So, when you are trying to compute the damage, you are talking in terms of the month, hour, layer, and then do the calculation. So, this is how this has to be done. Now, let us try to see how to compute the what to do with the climate. So, I am talking only in terms of the temperature quintiles, and in fact, I provided the explanatory text here just in case you are not able to follow it, you can read it by yourself. Let me explain. Pavement temperature within each thickness increment, okay, important sublayer, each thickness increment are calculated for each via the integrated climate model. I think you already know that it has already been discussed. The pavement temperatures are then combined into 5 equal groups assuming a normal distribution. The mean pavement temperature within each group for each month for each HMA thickness is determined for calculating the dynamic modulus as a function of time and depth of the pavement. So, that means you are looking at kth year ith month for the jth thickness increment. So, this is the quintiles that you are going to have. Okay. So, what you do is you use ICM, you determined for each and every thickness increment what is the pavement temperature. Then what you do, this pavement temperature that you are having, that distribution, you divide it into 5, assume that there is a normal distribution, okay, and then divide it into 5 groups, call it as quintiles, and for each quintile what you do, you take the mean pavement temperature and use this mean pavement temperature for each HMA thickness for computing your modulus value. Now, use this modulus value in your detailed distress computations. Okay. So, how do we do this, Julia? Of course, it is quite expensive. The whole Astover pavement ME design is expensive version, costs a lot. You can find out, and if you go to the website, you will be able to find out. There are many tools that are available. One is what is really called as the DRIP, that takes care of the subsurface drainage calculations. Then you have, means if you are living in US and if you are trying to do a pavement design for any county, what it will do is you can actually take the ME design project files based on the specific location. Then Julia and ICM are also part of it. Calibrator is used, and then you are talking in terms of where and what condition to use existing pavement as part of the pavement renewal pavement. So, RPAVE scoping is for renewal part, and of course, there is a back calculation also that is given here. So, now let us come to the distress part. So, you have done the sublayering, you know the quintiles that you have done, you have the Julia software for computing the stresses and strain. Now, they have to be computed back to the distress. Now, what is the first thing that you are going to do? You are talking in terms of the accumulated permanent deformation in a layer or sublayer. Of course, if you have many sublayers, you are going to sum it up. Okay. Now, that is delta P. Now, delta P is nothing but accumulated permanent strain, and this is the thickness. So, strain times the thickness of the layer sublayer, that is what is given here. Okay. I want you to pay close attention to few things here. Okay. What is epsilon r? Epsilon r is the resilient strain or elastic strain calculated by the structural response model. What is the structural response model? That is Julia at the mid depth of each HMA sublayer, right. Now, you should start thinking now, how is that you are trying to compute accumulated permanent deformation from elastic deformation, okay. Elastic strain. How are you computing the permanent strain from elastic strain? Very simple. What these people do, or what is normally assumed, is they assume that you have reached the resilient state. So, now go back to this picture that we drew before. So, this is your total strain, this is your number of cycles, okay. So, epsilon total, this is epsilon plastic, this is epsilon r. Okay. So, what you are saying is that plastic deformation and the resilient deformation are related to each other. My Julia program can compute only the elastic strain, that is computed here. Now, for me to find out the rut depth, I need the plastic deformation, and so I am going to use this whole bunch of other factors to take care of many other things. So, here I am assuming that resilient strain and the plastic strain are related to each other. Now, let us look at some of these parameters. These betas are what are really called as calibration factors. Okay. We can spend a lot of time on how to compute these calibration factors, we will not do it now. Then there is something called as the depth confinement factor, because confinement pressure plays a critical role in the response of the material. We have few publications related to the influence of confinement pressure on the stress strain response of the material. If you want, I can send it across to you. This is the axial load repeats, and K1s that you are talking about are called, one is called as the, so the betas will be called as local calibration factors, these are called as global calibration factors. Okay. One is with respect to the mixture, the difference in the mixture, another is with respect to the environment location in which they are being used. So, this is the model that you get for the permanent deformation of bituminous layer HMA. Now, let us see what we get for the permanent deformation of granular material. Now, the same thing, permanent or plastic deformation for the layer, that is given. Now, let us take this one epsilon r. In fact, different types of strain components are used. So, one is epsilon v, another is epsilon r, another is epsilon naught. Epsilon v is the vertical or the elastic strain, vertical strain. epsilon V and epsilon R is the resilient strain in the by the structural response model. So, this comes from the structural response model. This comes from computing epsilon naught and epsilon, and you are looking at epsilon naught is the laboratory experiment based model to obtain the material permanent deformation test. So, you can think of it this way, similar to what I explained. So, if this is what it is, so epsilon R epsilon, so that is what is given. So, this comes from the Win-Julia program. Then you also have the thickness of the layer here, then you have the density of the material here, and you have different calibration factors that are used here. So, this is the permanent deformation in the granular material. Okay. Now, let us go to fatigue, allowable number of axial load applications for a bituminous pavement and a HMA overlays. Now, this is the tensile strain at critical locations. Now, this critical location can be on the surface of the bituminous pavement or at the bottom, depending on whether you are talking about top down cracking or bottoms up cracking. Now, EHMA is the dynamic modulus. Dynamic modulus in compression Kf1, Kf2, Kf3 are global calibration factors, and similarly Bf, beta F3, beta F2, beta F1 are local. If you can do the calibration and set rate it to find it out, otherwise it is taken it as C1. Now, C is something similar to what you have already seen in your IRC calculations, and you can see from where your IRC equations are coming. So, I will leave these things here, because if I have to really discuss about each and every one of these parameters, how they are calibrated, how they are validated, it will take us few more hours. I only wanted to give you a brief overview of how these things are done here. Now, interestingly, MEPDG also introduced the IRA. Okay. So, what they wanted to do is, you can talk in terms of the functional distress. So, now if you take a look at it, so this is a side factor, so we will not worry too much about it. Now, this one, this is an interesting equation. So, RD corresponds to the average rut depth, TC corresponds to the transverse cracking, FC corresponds to the area of total fatigue cracking, and these are all related to IRI. Now comes the important question. So, which came first? Whether you had roughness in your pavement because of the rut depth and transverse cracking and longitudinal cracking area, or whether the roughness in the pavement induced this much of rut depth or transverse cracking or longitudinal cracking is something that we know. We do not know, and in fact, what you are looking at is having all of these things interrelated to each other. This is how it has to be, but this is what you can say, it is a work in progress. So, we really do not want to get into those particular details, but this is a tremendous amount of effort that has gone in terms of collecting this data and validating this data here. So, finally, we come to the reliability part. What is the expected reliability? 95%, 95%. So, you can actually see the arterials 90 and 85, collectors 80 and 75, local streets 80 and 70. So, how much is that? What is the design criteria? They say very clearly 10%. interstate. Interstate is, you can think of it like your national highway or expressways, it is 10%. So, what is the value that you use in IRC, you may want to think about it. Rut depth, interstate is 0.4 inches. So, that is going to be how much mm, and what is the rut depth that is allowed in Indian Roads Congress, that also you need to talk about. Then transverse cracking, do you have any criteria for transverse cracking? Think about it. What about IRI, what is the value that is given here and what is the value that is given in the Indian code? That is something that we need to think about it later. So, what I will do in the next lecture is to summarize the course and also give snippets, some snippets related to the design projects that one can do. Okay. So, till such time we meet, that will be the last lecture. Take care, work hard and see you soon.